Hi everyone, my name is Giacomo Cotelli and I'm a TADFsolutions Research Fellow. My research revolves around the use of 3D Kinetic Monte Carlo algorithms to model OLED devices, and for today, I'll be a stick figure. So the first question you may have is, okay, but what's an OLED device? And probably you may have one lying quite close by, namely the display of your phone, which zooming in is a quite complex structure with multiple layers having different functions, with the ultimate goal of course to emit light. Now, talking about physics, modeling these devices with one single formula can be quite complicated, if it's even possible at all to find one all-encompassing solution. Fortunately for us, however, the ingredients that we have to add in our simulation are not hard to model on their own, and we have individual theories that can describe each one independently. In detail, to model an OLED device, we must include charge transport, that is, the movement of charges across the device, the combination of charge carriers with opposite sign to form excitons, which ultimately decay to emit indeed light. Excitons again may move to the device, and we call this process diffusion. We must also include some processes by which excitons are however lost, for example by interaction with the charge carrier, formerly known as polaron, which is said to quench the exciton by absorbing its energy, which successfully gets dissipated, thus destroying the exciton. An exciton may also interact with a second exciton, which again absorbs its energy and dissipates it, thus resulting again in a loss. Now, theory allows us to describe this process in terms of rates, linking to the probabilities of each event taking place. But how to put this all together? Monte Carlo methods take a really straightforward approach to that. Like in the namesake casino, you take a die and throw it, and repeat the process over and over and over again. In more scientific terms, since we have the probability of each event taking place, we can use random number generation to evaluate the evolution of the system in time. Eventually we get something that looks like this. We have a grid of points which represents our device, on which charge carriers and excitons can hop, diffuse, and interact. But what we actually want to get from the simulation is the list of events taking place and at which time and where. And this is the rich source of data which a Kinetic Monte Carlo algorithm can provide. By analyzing this data, we can get some result on the overall behavior of the system. All in all, if you allow me an analogy, Kinetic Monte Carlo methods, or KMC methods for short, are themselves a kind of box in which we can put any kind of physical ingredients besides the standard ones I already mentioned. My objective in this project is indeed to investigate what more can be done with KMC methods to get more advanced and more reliable results, with the double aim to use simulations to both clarify and get deeper insight on experimental results, or to probe in regions where experiments cannot yet go.